Development of a software based on IEEE 80 to 2000 standards and available on Android devices, to design ground meshes in high-voltage substations. Abstract. This application was designed and programmed for the efficient design of the ground mesh protection system to safeguard the lives of people, animals, and vegetation, as well as the useful life of each of the elements found in an electrical substation. This is based on the IEEE 80 2000 standard, which gives us a guide for safety in AC substations. The professional in charge of the project and who will use the application, must use the Wenner method to obtain a maximum number of measurements equal to 7, and for each measurement it must be repeated 3 times. With this, the application will indicate if the terrain is homogeneous or heterogeneous. As a second step, the application will calculate the gauge of the conductor that will be used in the real area where this protection system will be implemented. After this, the application will find the step and touch voltage values, important parameters in this type of protection system. And finally, the electrical resistance of the mesh, the total number of rods to be used, among other data, will be calculated. At the end of all these steps, the application provides a report where all the values found and necessary for the implementation of the mesh are found. Said report will be saved in the internal memory of the device in which the application is starting. Keywords: ground mesh, IEEE 80-2000 application, touch and step voltages, Wenner's method. Introduction. In the engineering area, specifically in electrical engineering, there are various points of electricity generation, which is transported by high voltage lines and also elevated or reduced in substations. In the latter, there are large power transformers. It is due to these machines and their high cost, that designers find it necessary to implement the ground mesh protection system, in order to guarantee efficient work of the machines and of course, preserve and safeguard the lives of all living things. As mentioned above, there are various standards to comply with this, but the one chosen for the construction of the application is the IEEE 80 2000 standard, which provides us with a methodology to design ground meshes in substations, this with various formulas, graphs, tables, etc. Despite this, there are some professionals in the field who do not follow this or any other guide for the design of this protection system, that is, they do not make a preliminary study of the terrain and only assume values such as resistance, resistivities, heights, among other parameters, which can lead to inefficient work and in the worst case, the death of those involved and mentioned above. 1. Function of the application. Define the type of terrain. The application will show spaces to complete resistance values obtained by the user through measurements with the Wenner method, maximum 7. In case the user makes fewer measurements, there will be no need to complete them with 0 since the measurements not completed will not affect the subsequent calculation. The application will calculate the resistivity values based on the values entered by the user and through the following formulas. The user enters the value of the symmetric fault current, which is the maximum short circuit current, in kiloamperes. Short circuit current of the system allows to establish the characteristics of the protection elements that must withstand or cut the fault current, so that it is necessary to perform the calculation for each of the voltage levels of the system. 7. The duration of the ground fault current in seconds according to the electrical concessionaire and the ambient temperature of the design. These parameters are important since the gauge of the conductor cable must withstand them in order to maintain continuity of service. At this stage, 2 important factors must be calculated, which are directly related to the safety of people. These factors are step and touch voltage. The term touch voltage refers to the potential difference between the ground potential rise, GPR, and the surface potential at the point where a person is standing while at the same time having a hand in contact with a grounded structure too. Likewise, the tension of step, when current is flowing from an overhead conductor through a chain link fence to the earth, a high voltage condition is created and a voltage gradient will occur based on the resistivity of the soil, resulting in a voltage difference also known as a potential difference between 2 points on the ground. This is called a step potential as it can cause voltage difference between a person's feet. When choosing the square mesh, the value of the mesh side in meters must be entered, in addition to the vertical and horizontal separation distance, dy and dx respectively. If it were rectangular, it is the same procedure, only the length, lx, and width, li, values must be entered of the mesh, since in this case both sides would not be the same as it is in the square mesh. If it were the case of an L-shaped mesh, you must enter greater and lesser length and width values, that is, for values and their respective separation distances. To calculate all the variables involved in the mesh current, the user will enter the value of the X/R ratio depending on the characteristics of the substation. In addition, the application will allow to choose the approximate equivalent impedances of the power lines, guard cables, transmission and distribution neutrals. Then, the number of transmission lines and the number of distribution neutrals must be chosen. This last piece of information is one of the most important at this stage, since it allows us to know the exact value of SF. Since only some SF values are predetermined for various combinations of transmission lines and distribution neutrals, and in order to know the exact values of SF in all possible combinations between number of transmission lines and distribution. But to know the equivalent impedance value of an uncommon combination of transmission lines and distribution neutrals, for example 1 and 3 for a RTG of 15 ohm and ridge of 25 ohms, it was interpolated taking as an upper limit the values of combination 1A2 and 1A4, thus the equivalent impedance was calculated and replaced in the formula 22. This was the criterion for calculating the value of SF. After entering the X/R value, choose the RTG or ridge value and select the combination of number of transmission lines and distribution neutrals. The user must answer the question, do you consider the total capacity of the substation and in the future keep the load and feeders constant? If the answer is affirmative, the value of CP will be equal to 1, since the load will remain constant over time and the total area of the substation is being considered without projections to increase. Otherwise, to a negative answer, the user must enter the percentage, for example 15%, in which he plans to increase the total capacity of area or load, then CP will be calculated with the following formula 5. After the application has developed all the implicit formulas within the mesh current, it will show in a partial report, the touch voltage values, symmetric fault current, reduction factor for the entire fault duration, current division factor, mesh current, ground potential rise, GPR. GPR is equal to the grid resistance times the current maximum grid. Besides, GPR is the maximum electrical which attained relative to a distant grounding point as at the potential of remote Earth. 8. Correct design, but consider to apply some treatment to reduce the resistance of the mesh to the ground by 80% in case the resistance of the mesh is greater than 1 ohm, in order to respect the measures set by the IEEE 80 Regulation 2000. As a result of the message mentioned above, the design will culminate showing a final report. This report shows the sections of type of terrain, conductor gauge, tolerable tension criteria and mesh resistance. In addition, the final report can be saved on the user's device for future studies or analysis. Method for calculating soil resistivity. Since the IEEE 802000 does not include a specific method for calculating soil resistivity, it was necessary to resort to investigating various types of evaluation for it. Concluding in various comparisons, that the most correct method based on theory and calculation is the tag method known as the tag equation, through which I determine some master curves that simply consist of giving values to the variables k, h, and a, obtaining values of /1 for each case. It is necessary to comment that k varies between -1 and 1, that is to say that for k values between -1 and 0, results of /1 greater than 0 and less than 1 are obtained, which corresponds to the fact that the first layer has a resistivity greater than the second. For k values between 0 and 1, the values of /1 will be greater than 1, since the resistivity of the second layer is greater than that of the first. Conclusion. Achieving an optimal design of a ground mesh does not depend solely on the characteristics of the electrodes but is active on the terrain where they are located. In this article we show the development of a software that can be used on a mobile device, which leads to the design of a ground mesh so that in cases of electrical discharges or overvoltage, the current finds a safe route and thus avoid damage to a being alive or nature. The resistance of the mesh depends on the lengths, cross-section, and shape of the electrodes. The application has been programmed to give as a result the dimensions of the electrodes, touch, and step voltages, among other parameters and shown respecting the IEEE 80-2000 standard. At the end of the design, the application will suggest applying a chemical additive with which it will improve the results. This notification will be displayed regardless of whether the results obtained are optimal or not.